Okay, we're going to start Chapter 2 now, and Chapter 2 has to do with linear functions. And linear functions are a relatively easy process to understand. The term linear has the word line in it. And so these are line functions. And what you're going to be doing is that you're going to be graphing. You're going to be using an equation. The equation that we're going to use is perhaps the most famous equation in all of math. It's y equals mx plus b. Y equals mx plus b will be used as we find out what the slope is and the y-intercept. As we study this equation, y equals mx plus b, we're going to find out that the slope is that right there, and the y-intercept, or where it crosses the y-axis, is right there. And we're going to learn all sorts of fun things about this equation. You'll see it over and over and over again, so get used to seeing it and get used to working with it. Okay, first page of the book, really, I think you have, here are the key terms, the sequence, and what a term is, and an ellipsis. We are going to spend a lot of time with sequencing. We're going to talk about perhaps the most famous sequence of all, called the Fibonacci sequence. And I'm going to show you a video that deals with the Fibonacci sequence and something known as the golden ratio. It's a really pretty cool video, and I'll play it for you one time, and then we'll talk about it, and then I'll play it for you again so that you get an idea as to what it really is trying to say to you. Okay, on the previous page, it talks about placing coins on a checkerboard. I decided not to really discuss that with you too much because we talked about the emperor and the 1 grain of rice, which we changed into 1 penny, and we saw how quickly that grew. You do the same thing to a checkerboard with a coin. It's going to add up very, very quickly. But I told you we're going to talk about the Fibonacci sequence, and so let's discuss what it is. It looks like this. Starts off with a 0, then a 1, and another 1, and then a 2, and then a 3, and then a 5, and then an 8, and a 13, and then I'm going to put in the ellipsis right there because it continues on. And what we want to show here is that this sequence is, if you haven't seen what's taking place, you just add the 2 previous numbers together to get the third number. So if I look right here, if I go 0 plus 1, it gives me 1. If I go 1 plus 1, it gives me 2. If I go 1 plus 2, it gives me 3. 2 plus 3 gives me 5. 3 plus 5 gives me 8. 5 plus 8 gives me 13. And 8 plus 13 gives me, and I'll let you figure out what that is. Well, this particular sequence, whether the early people that were artists and architects and people that worked with beautiful things understood this sequence or not, they did indeed use this to create beautiful objects. And we're going to talk about those. And like I say, I'm going to show you this video, and you should understand it. It's a really cool video. So I'll show that to you in class and give you a chance to see where things end up in terms of this golden ratio. Okay, here's our first set of sequences. A sequence is a pattern involving an ordered pair. A term is a sequence of an individual number, figure, or letter in the sequence. So we have some very simple sequences here. 2, 4, 6, 8, 10, 12. A sequence that's geometric, showing different shapes. 3 sides, 4 sides, 5 sides, 6 sides. Another sequence, sequence C, is A, B, C, D, E, F, G. And then sequence D is a sequence of arrows pointing. You'll notice at the end of each one of these there's something known as an ellipse. These three dots here, or an ellipsis, sorry I said that incorrectly. An ellipsis, the dot 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 means it goes on forever and ever and ever, and it can stand for, and so on. So you got some questions to answer here. I want to take a look at problem number 4. Down here, the 12th term in sequence D. What would be the 12th term? You take a look at this. I've got these 4 arrows, and then it starts over again right here. So you can take 4 into the 12th term and determine which arrow or which direction the arrow is going to go. You could go into the 5th and figure it out by dividing 5 into 12. So there's a couple of options that you can look at and different ways to determine what the 12th term is in the sequence. You're going to find a pattern here, and probably we're going to come up with an equation that will help you figure this out very quickly and very easily. Here we have a sequence of designing a beaded necklace. If you've ever been to any of the Indian reservations or to an Indian store where they are selling jewelry, you'll see this happen over and over and over again. A lot of turquoise, a lot of silver. They do beautiful workmanship. I don't know if you've ever been to the Four Corners area of Utah, Colorado, New Mexico, and Arizona. If you ever get a chance to go there, you'll see a whole bunch of the Indian nations surrounding the Four Corners area, and they are producing these beautiful beaded necklaces, bracelets, hats with beautiful beads on them. It's quite an art, and uses sequences and patterns. And so here we are trying to be a Navajo Indian or a Ute Indian. Go Utes, you know that. And we want you to create a necklace following the example that is being set right up in here. Follow those steps and create this necklace and place the beads in there. You may have to draw something. Maybe some of you can do it in your head, but you may have to draw something to see what the sequence is going to be and what the pattern is going to be like when you finish this necklace. This is a sequence of creating toothpick houses. Just to help you out with this a little bit, when you do this, the first toothpick house that you build is going to have 6 sides. 1, 2, 3, 4, 5, and 6. But the next one you're going to build won't need 6 sides, only 5 sides. In this one it's going to be 1, 2, 3, 4, and 5, because this side is already built. And on it goes. And so you're going to have this sequence. The first one's going to be 6, then 5, 5, 5, 5, 5 after that. And you can either get toothpicks or you can draw them yourself and see how to create this house and what's going to take place and how many toothpicks you're going to need to build X number of houses. What you're going to do in this example is that you're going to start removing cards. And when you remove cards, you're going to have cards left. And what you're going to do first is you're going to remove this row or that column and this row and count how many you've removed and how many do you have left. And then you're going to remove this and count how many total you've removed and how many you have left. I think as you do this and you count them, you're going to see a pattern develop. And you ought to start to think, now, if this is the case, how many each time? Is there an equation or is there a formula that I can look at that tells me I remove these, that means I'm going to subtract. I'm going to remove these, I'm going to subtract again. What's the total that is left? And hopefully you can see this pattern develop. We'll talk about this when you start working on this in class. Okay, can you follow what's happening with arranging these pennies? What's being added at each different row. And again, just answer the questions. Realize the next line is going to be, and I'll let you figure that out. We're going to be building some stairs, and I'm actually going to have blocks available for you in the classroom where you can stack these and create these stairs. It asks in this particular problem about the number of faces that are being shown. In this one, right here to begin with, you need to know that there are 3 faces. 2 that are white and 1 that is black. In this next one over here, there's going to be 1, 2, 3, 4, 5, 6, 7 faces. You're going to have 2 that are black and 5 that are white or blank. When you get the blocks, you're going to want to set it up just like this, so that it's on this bit of an angle, so that you can count the faces and watch the progression of what takes place as you build the stairs. Hey, now that I've talked about the number of faces that are showing, you can see them, but on the first cube there are 2 that are not showing. The bottom one is never counted as a face. And I don't know if I can draw this very well, but there's a face back there and a face back there that are not showing but are still considered faces. So when you count the number of faces in this next one, remember that there are faces on the back side and how many of them are actually showing, remembering that the faces that are on the ground or on the floor or on your desk as you build this thing, those faces don't count. This page just talks about arranging the classroom tables. If you happen to have a trapezoid table, then you can put them in all sorts of different shapes. We don't have that situation. Ours are just rectangular, so we're fairly well set with what we have to see here. But you can see that you can rotate these, put them like they've done here. You can put them, put one sort of here if you want. I didn't draw that very well. Back to back, face to face, all sorts of different things that you can do there. On this one, you're going to create a petal, or a flower, I should say, and you're going to draw different petals around this dot. So you're going to fill out the data at the top, and then you're going to start to draw the petals and explain what's going on as those petals get added to it. These 2 problems, you're going to go babysitting, and you make $14 on Friday, and you spend $10 on Saturday. Give me an equation or what is going to happen after 5 weeks of doing this. The recycling, we do recycling here in the school, and we're going to, in this case, they're going to recycle cans. There's 120 of cans per week, and determine how many cans for the first 9 weeks of school. That's a pretty simple mathematical problem. Okay, now in this one we're going to be selling tickets. If you think about the dances, if you've ever been to a dance, I take the tickets at the dance and take your money. We don't sell you tickets, we just give you a stamp. And I always bring some money with me so that I can begin to make change, and then as you kids come in, you give me enough money that I can make change easily. For those of you that bring in the crumpled up $20 bills. So write a sequence to show the amount of cash that Sam has available, and then what happens as he starts to sell tickets. Then the talk, that goes without saying. I shouldn't have to say anything about it. Okay, on this page, what we have is a table that you will use in the information that you've already created about designing a necklace and the toothpick house and the card trick and all that sort of thing. You're now going to fill out this table, tell me whether things are increasing or decreasing, and describe the pattern. When you describe the pattern, don't do it in just 1 or 2 words. Explain to me what is taking place. Take the time to write it correctly. Some of these will be fairly short, others will be longer. Like Every time I add a sequence, I add 1. Or every time I do a sequence, I'm adding 4. Or something that is taking place. Or as I do a sequence, I'm removing or subtracting 1, especially in the card trick one. So you're going to be either increasing or decreasing, and then write as much as you possibly can, clearly and precisely as to what's taking place, adding or subtracting parts to the sequence. Okay, in section 2.2, what we're going to have is a little bit more detail in terms of the terms that we want to use. We're going to talk about a discrete graph. A discrete graph has dots on it like that. A continuous graph will have the dots connected. A linear graph is what I've just drawn here on this particular one. A linear graph is a straight line. Collinear points, these right here, they are discrete, but because they are in a straight line, they are collinear. They're on the same line, and if I were to connect them up and make this graph continuous, they would form that line. And then the last thing you have is a nonlinear graph, and it looks like this: point here, point here, point here, point here. Yes, I can draw a line between the 2 points, but when I do draw the line, you'll notice that it does not stay in a straight line. It's here, then it's here, then it's here. So 3 different locations. That would be nonlinear graph. Okay, this needs a little bit of an explanation here. You've got the 4 terms, 0, 2, 4, 6, and 8, and they want you to graph this. It's a little misleading. They want you to put these on here. They want the 0 to be position number 1, so it would be these terms 0, 2, 4, 6, and 8 are the x terms, so it would be 0, 1. The next term is going to be 2, 2. The next term is going to be 4, 3. And the next one is going to be 6, 4. Those are the ordered pairs that they want you to use. If you read it, it says, let the term number represent the x-coordinate, and let the term value represent the y-coordinate. This is x, and this is y. Okay? And so here's the term number, 0, 2, 4, 6, 8, and here's the term value, 1, 2, 3, 4, as it is in place. Place 1 is 0, place 2 is 2, place 3 is 4, place 4 is 6. Here we have the definition of a discrete graph. I already showed you what that was. A discrete graph is isolated points. A continuous graph is a graph that has those points connected. On this page, we're going to cut these graphs out, and then we're going to start to place them in groups and state whether they are continuous, whether they're linear, even discuss if they're a function or not a function. On this page, you've got some tables. Which one of the previous graphs are discrete? Which one of the previous graphs are continuous? Are they increasing or decreasing? Do they both increase and decrease? And are they neither increasing nor decreasing? And then what you have is the bottom one. You have a linear graph and nonlinear graphs, and you'll just be picking from the graphs before that on the previous page and placing them in here. In terms of increasing and decreasing, we read them from left to right. So if a graph is going up from left to right, it's increasing. If a graph is going down, it's decreasing. Okay, problem 2 has us reading a graph. Greg is going to get in a car, travel for a while, take a rest, travel for a little bit longer, take another longer rest, start to return home, take a rest, and then end up someplace but not back at home. And so using the numbers on the x and the y axis, as you have understood, time is generally always x, and the hours or distance, or I'm sorry, not the hours, but the miles or distance is always, or nearly always, y. And so they're going to ask you to count the numbers and answer some questions, after 2 hours of traveling, after 3 hours, and so forth. And so you need to interpret this graph. On that previous page, they're going to want you to label the graph. The first segment is going to be labeled A. Then he's going to rest, and that's going to be part B. And then you go ahead and finish C, D, E, F, and G, and label them, and then fill out this table, talking about the time interval, and then explain here as to what is taking place. Explain right in here, write down what is happening at that graph. He's traveling for how many hours, and it looks like he went so many miles. Again, don't shortcut this. Explain what's taking place. We're going to do the same thing with this graph. We're going to drain a swimming pool, and then we're going to fill it up, and you should be able to interpret what is taking place with the swimming pool. Fill out this chart in relationship to the swimming pool and being emptied and then filled. Again, in the description, make certain that you write down everything that needs to be written down. Don't shortcut it. And so now you're going to go to the movies, and you're going to buy a box of popcorn. Explain to me what you think is happening in problem number 1 here. How is the popcorn being eaten? In problem number 2, how is this being eaten? Write it in your own words.